We have looked at enzymes, Michaelis-Menten enzymes, allosteric enzymes, just a little bit, and what we want to talk about now is enzyme inhibition. So we want to be able to recognize different types of inhibitors based on their kinetic parameters. So enzyme inhibitor is something that, as it sounds like, will slow down or stop the enzyme from working. And the kinetic parameters, let's go back and review. Here was our Michaelis-Menten equation, and we're going to really go back to those Michaelis-Menten, the simpler kind of picture of enzymes for now as we talk about these inhibitors. Later, we'll talk more about regulation of some of those allosteric enzymes. Okay, Michaelis-Menten Michaelis-Menten equation, hyperbolic. And remember that we could find two main kinetic parameters. We had the Vmax, so that maximum velocity, maximum reaction rate. And we know that that was equal to that kcat times the total enzyme. So that kcat, that reaction constant, and Vmax kind of go hand in hand. And then we also looked at the Michaelis-Menten constant. And so when we think about this, these top two, the kcat and Vmax, tell us something about the turnover rate, how fast product is made. If we go back and we think, remember our Michaelis-Menten picture, we have the enzyme plus the substrate, forming an enzyme-substrate complex. And then that enzyme-substrate complex will form those products, and we'll get our free enzyme back. So the kcat and Vmax tell us something about this rate of reaction right here. How fast does this go to products? Km, on the other hand, told us about the substrate-enzyme interaction, right? It was something about the bonding affinity, how likely and how strongly this enzyme and substrate bond into this complex. Now, as we talk about inhibitors, this could be some small molecule, some drug, something that's going to change some of these parameters and change how this whole process works. All right, let's remember that we talked about the Lineweaver-Burke plot, and that is really useful because it linearizes our data. It makes it easier for us to see. Okay, so if you remember, this is a double reciprocal plot. So now instead of plotting the velocity of the reaction, we're doing 1 over velocity. Instead of the substrate, we're doing 1 over the substrate. Okay, and when we did this, we highlighted this point. We said, wow, we can use that x-intercept to find the Michaelis-Menten constant. We highlighted this point because we said, wow, we can use that y-intercept. That's going to tell me something about my Vmax. And we looked at the idea of the slope, right, is Km over Vmax. So if we knew one of those and we measured the slope, we could find the other. So let's look at a couple of these data points because it's going to turn out that this graph is going to be a great way for us to identify what type of inhibitor we have. So we said here is our y-intercept. But what if we graphed our data after adding an inhibitor and we found our y-intercept was now there in our new graph? Okay, so if that's true, we know we're getting a larger value here. So does that mean that my Vmax has gone up or gone down? And since this is 1 over Vmax, we must have a smaller maximum velocity, and hence 1 divided by it gives us a bigger value, the one in green. All right, let's compare 2 points down here. If this was my original x-intercept, and now let's say my x-intercept is here, closer to that origin. If I think about that, this would also be negative 1 over km, but we'll clearly have a different km value for this second round. Okay, and when I look at that and I think, wow, I'm getting a smaller value here, km must be larger. All right, so if this was my new data, and I plotted that, I'm going to come up with some different line there. And that line would tell me that, you know what, whatever I added to change this, I have changed my maximum velocity, it's now lower, and I have changed my affinity for the substrate, that enzyme substrate complex. I'm sorry, yes, I've changed the affinity, and if Km is larger, we know that that affinity is decreased because those were reciprocal. Okay, so we're going to be looking at that a lot. Let's look at one more example before we go on and look at the inhibitors. So this graph shows the effect of two different concentrations of molecule X. So X is not our substrate. We're still graphing our substrate, 1 over the substrate, versus 1 over that reaction velocity. So X is something else, okay, that we are adding. And we added some here, and we added even more here. And we see that it's changing. And my question is, how does that change our parameters? So we're going to talk about Michaelis-Menten constant, and we're going to talk about that maximum velocity. Well, when I look at this, I see no change of that x-intercept. So we see no change in that bonding affinity for the enzyme and substrate, forming that enzyme substrate complex. But I see I have new y-intercepts. So I know that I am seeing a change in my maximum velocity. And I can look at that and say, wow, the more of this molecule I add, the higher I'm going up my y-axis. So when I think about that, I must have a smaller and smaller maximum velocity reduction in Vmax. All right, so we are going to talk about 3 specific types of inhibitors. We are going to talk, and so here we're saying reversible inhibition. So when we say reversible inhibition, we mean that that inhibitor binds and releases. So whatever that small molecule is, it can bind to our enzyme, but it can also release. So it's on and off. It's not irreversible. We'll talk about that briefly at the end. Irreversible would just shut down our enzyme. So we have reversible inhibition, and we're going to talk about 3 types. We are going to talk about competitive inhibition, and this is one where whatever the inhibitor molecule is similar to the substrate and can bond at the active site. So they're competing for the active site. Once the inhibitor's there, the substrate can't bond. There's no space for it. All right, we can also talk about uncompetitive inhibition. So now we're talking about the inhibitor binding to the enzyme substrate complex. So the enzyme and substrate are already bound, and so the inhibitor must bond at a different site. So 2 different bonding sites, one for the inhibitor, one for the substrate. We will also talk about non-competitive inhibition. So in this case, the inhibitor doesn't care. It can bond to the enzyme substrate, or to the enzyme alone, or the enzyme substrate complex, right? It's not picky. So it can bond before or after the substrate has bound. We're going to look at pictures of each of these. All right. There's also one called mixed inhibition, which is kind of a combination of competitive and uncompetitive, and that's really a combination of uncompetitive and non-competitive, a little bit beyond the scope of the course. So we're not going to worry about that one. All right, let's look at competitive inhibition. So we have 2 possibilities. So first of all, let's orient ourselves. So we know that the enzyme and substrate will bond into the enzyme substrate complex. And we're showing that right here. All right, so this is what I'm showing in this box. So we have the enzyme. It has this active site, and the substrate shown in yellow bonds to that active site. But another possibility is that instead of the substrate, what if we have an inhibitor that has a similar shape, a similar structure, and it can bond in the active site? So now we still have our same enzyme, and now we have our inhibitor molecule that is bonding, and once it's there, it's blocking it, right? Our substrate can't get in there. All right, let's think about what this would look like, because of course we can't look and just see these molecules, see this bonding, see, yeah, they're not actually orange and yellow. So how do we know if we have competitive inhibition? Well, we're going to look at all that kinetics data. So we are going to come down here, and we've got our velocity times our versus our substrate, and when we look, we know we're going to get that kind of hyperbolic curve. And so this would be with no inhibitor. And in the presence of our inhibitor, there's these two options, right? Sometimes the substrate will get to the enzyme first. Great, we get our enzyme substrate complex, and then we know that enzyme substrate complex can continue on to form enzyme plus product. But sometimes the inhibitor gets there first and blocks it, and then this cannot go on to form product. So if I think about that, remember that this is reversible, right? That inhibitor is going to go on, but go off, go on, go off, go on, go off. And so if you think about it, eventually every time that inhibitor comes back off, there's another opportunity for that substrate to sneak in there and grab that active site. So eventually we can still get to the point, to that same maximum velocity. Okay? It's going to take more substrate, but essentially if we increase the substrate concentration a lot, then we increase the statistical odds that the substrate will be one to grab that active site, and we can still get to that same V max. So if I was going to look at that now on my graph, I might show it something like this, right? Where it's going to take more substrate to get to that same place, but I can still, with the inhibitor, still get to there. Let's look now at our graph, though, now that we've drawn this. We know that Km numerically is the substrate concentration at half Vmax. So here was Km for no inhibitor. But if I look at half Vmax, notice it took me a lot more. It changes because it changes the affinity of the substrate for the enzyme, essentially. The binding of the enzyme to the substrate isn't as good, right? Because sometimes it can't bond. Sometimes that enzyme is all blocked. And so we see that Km is increasing, which means lesser affinity. So that makes sense. Let's think about what that would look like on a Lineweaver-Burke plot. So if I had an initial plot that looked something like this, no inhibitor, I know that my Vmax is going to be the same. So I'm still going to have this spot. But I know that Km is increasing, so 1 over Km would be closer to the origin. So I'm going to see a new line with a different slope. Okay, and this would be with the inhibitor. that looks like that. So if I saw these kind of crossing lines with the same y-intercept, I could say, wow, that's a competitive inhibitor. All right, let's take a look at uncompetitive inhibition. So now we have an inhibitor that doesn't bind to just the enzyme. It will only bind to that enzyme substrate complex. It'll obviously have to bind in a separate spot because the active site's already taken. All right, and remember we could continue this, right? Up here, this could go to enzyme plus product. But this down here cannot go to enzyme plus product. That inhibitor is keeping that from happening. So by the time we get to this point, we got two options: enzyme plus product or enzyme substrate inhibitor down here. All right, so let's think about how that will affect the Vmax and the Km. So first of all, let's come put in our baseline again. So we've got something like this for no inhibitor. I've got a cat walking across my iPad, so that is not helping with the video. And we would have something like this straight line plot for no inhibitor. All right, let's think about how this works. When the inhibitor, first of all, let's just think about the Vmax. That one's probably a little easier. Even if you increase the substrate concentration, so if we increase substrate concentration moving to the right, since the substrate has bound first and the inhibitor bonds second, that extra substrate isn't overriding the inhibitor. It's not like up here where, wow, if we just overpower, then most likely our enzyme substrate will get that instead of enzyme inhibitor. Here, the substrate's bonded either way. The substrate, we can't overpower that inhibitor. And so what we're going to see is when we get to this complex, now only part of it can go to products. Part of it is going to get tied up. And so we have less of this complex available at any point in time to go to product. And so we are going to see now a lowering of our Vmax. Okay, so we know now with, and I'm going to come back to the rest of that, with our inhibitor, we'd have a lower Vmax of some amount. Now let's think about the Km. Km is a measure of the affinity of the enzyme for the substrate. But I want you to stop and I want you to think about Le Chatelier's principle. If we have this equilibrium, and then some of this enzyme substrate gets pulled, right? So, and I should do a different arrow there just so it's not confusing. Some of that enzyme substrate gets pulled out of the equilibrium because it gets tied up as this. So the amount of this is going down. The amount of the ES is going down. And we know Le Chatelier's principle says, well, hey, if you pull out some of the product, that's going to shift my equilibrium to the right, make it more likely for the enzyme to bond some more substrate. So because of Le Chatelier's principle, it makes it look kind of artificially as if the enzyme and substrate have a stronger affinity, because we're going to see more and more of the enzyme bound up. And we know stronger affinity, even though it's kind of an artificial result of Le Chatelier's principle, a stronger affinity would mean a smaller Km value. So let's actually come back over here. Let's look at our Lineweaver-Burke plot first. So if I'm going to have a lower Vmax, I know 1 over Vmax would now be higher. And if I am going to have a lower Km, higher affinity, I know, and I didn't leave myself room, did I? I know that this x-axis intercept would have to be further out, right? 1 over Km, if Km is smaller, is going to give me a bigger number. And what we see, and I probably haven't drawn it perfectly, is we end up getting two parallel lines. Sorry about that. Two parallel lines, and so this would cross the x-intercept somewhere here. Did not leave myself enough room. When we see that, we're going to think, wow, that's an uncompetitive inhibitor. I see that I have both a lower Km, and this would tell me I have a lower Vmax. Lower Vmax. All right, let's come back over to the left now and look at it on this plot because it's a little harder to see here, but let's mark Km, the substrate concentration at half max velocity. So here is Km for my non-inhibitor. And I know I need that Km to be lower. So that Km has to be somewhere back over here. And if I look at where I drew this, well, halfway would be kind of here, right? So halfway might be right here. So, and it's going to be hard to see. We would usually use Lineweaver-Burke, but you can see something like that would be our graph. All right, one more, non-competitive inhibition. So we get even more pictures with this one. All right, inhibitor bonds to a site other than the active site, just like with uncompetitive, but now, before we had it bonding just to the enzyme substrate. And notice that this is a little bit different. This here is now vertical. Up here it was horizontal. So we've got the enzyme. Here's our this. If we wanted to continue our Michaelis-Menten, we could say, oh, and that could go to, whoops, that needs to be two different ways. That could go to enzyme plus product right here. But it turns out that at either of those steps along the way, when we have just the enzyme, the inhibitor can bond and block. So now it doesn't matter, even if the substrate bonds, this is not going to react to form product. It can also happen after the substrate. So inhibitor can inhibit the enzyme action whether or not there's substrate bound. Okay, it distorts the active site to inhibit this reaction that takes us to the product. So we essentially have a couple different ways this could happen, right? We could have the enzyme binding with the substrate. Oh, we get the inside substrate complex. And now that could bond with the inhibitor. And when we now we have this thing that cannot go to product. Or the enzyme could bind first with the inhibitor, and then it could bind with the substrate. Yet again, cannot go to product. The only place it can go to product is right here. Okay? If that enzyme substrate complex manages to finish the reaction and go to product before the inhibitor gets to it, we can still make some product. Okay, so since the substrate can bond to either of these, to this or this equally well, Km is not affected. So that affinity is the same. But since that inhibitor keeps the enzyme substrate complex from going to products part of the time, right? Sometimes it can go to products, but sometimes it can't. The maximum velocity will be reduced. So we can't achieve the same maximum velocity. All right, here was our original no inhibitor. Here is our original no inhibitor. And then when I think about this, I know that my max velocity with the inhibitor will be lower. But I know this time I'm going to have the same Km. So if I look at the half max velocity for the no inhibitor, it's right here. I know that my half maximum velocity for the inhibited one, I would start here, I'd go about halfway. All right, so I know that I've got to cross this point because I need to have the same Km value And so now I've got something that has same Km, but has a lower maximum velocity. If I come over here, I know same Km will mean the same thing here. I need no lower max velocity will mean a higher y-intercept. And so with the inhibitor, I see something that looks like that. All right, that was a lot. So what you're going to see on the next 3 slides is just kind of what we talked about, but more neatly typed up and drawn. Oh, actually, yes. So you can take a look at all of these graphs. Here it is for uncompetitive inhibitor. Here it is for non-competitive inhibitor. So the only thing we haven't talked about is irreversible inhibitors. So an irreversible inhibitor, once it bonds to the enzyme, it's done, right? It is not going to release. It oftentimes bonds really tightly with some sort of covalent bonds, shuts down the enzyme. We're not going to get products. So we don't have any kinetics data. Like we can't graph these same graphs because there's no products to measure. These are really useful for helping us figure out mechanisms of reactions. So picture, for example, if you wanted to figure out which amino acid in a polypeptide was the amino acid that really interacted with the active site of an enzyme. Well, one thing we could do is we could let some of this protein interact with our enzyme, and then we can add an irreversible inhibitor, but we can add one that we've tagged somehow. It's got a fluorescence tag, a radioactive tag, something where we're going to be able to find it. Because we know that an inhibitor will bond to our enzyme, and if we stop it while the enzyme is bound to that protein, we can then analyze it and figure out which of those amino acids was in that enzyme. So we can use it for stuff like that. All right, that is it for this video.